Hello. Hi, Professor Nottingham. Can you hear me? Yeah, somehow I can't hear you. Let me see. Oh, I can hear you now. Great.
Can you hear me now?
Yeah, it's my bad. All right.
Yeah. So this is Bill basically said it's the end of the um, it's towards the beginning of the new semester. So all the PMP projects are being completed, and he has to attend, I think, presentations and whatnot.
Yeah.
Do grading and attend presentations. So he's busy today, unfortunately, because of the capstone projects.
Yeah.
So he will have to exit, not attend today, but one thing that so he can still send the email off to talk to Noah Flux if there's any specific things that you want him to address with with them. Is there anything in particular you want him to discuss with Noah Flux and kind of communicate with them?
Yeah. Actually, yeah. Regarding last time we talked about the Nipro. There are only two of them, so there might be an issue that when we file the Nipro and that we don't have enough Nipro. But after I think a little bit more, so because right now we still have about six of the 5 or 6 of uh, the the Rexy 21R. I was thinking that might be a good, like, we can use it as uh, what should I say, a replacement for Nipro, that we can like start doing some filing experiment on the Rexy 21R first, because we can get the sieving coefficient from there and then use it as a benchmark to compare inside out and outside in. I think that's not a problem with the Rexy 21R, and I think the effect of the Rexy 21R is gonna be good enough to get an estimation for the Nipro. So I don't think we should probably ask for more Nipro at this point, just from my opinion, that we can just utilize the Rexy 21R first. Yeah, and I think if you're trying to get an update with the HPLC, I think we are doing not a calibration, a standard to see whether the HPLC is going to work for our experiment. But I have talked to Dr. Antonio. He's a PhD. He's a postdoctor at he's working on a similar project of mine, also using he's not using Dastran, but he's using this kind of aqueous solution to purge in the HPLC. And yeah, so I think he has really good experiment, and his comment on my experiment is probably gonna work, but we're just gonna tweak around the setting. And currently the HPLC at the at the lower, nobody is using it, and Lindsay, the lower agents I've been contacting with, she told me that we are able to use this machine like no problem, no conflict, and everything is setting it up. You just need to pay the injection fee. No equipment, probably no equipment needs to purchase. On top of that, injection fee. Yeah, so that's probably the update for the HPLC. I don't know if.
And one thing I want to ask is, okay, so what exactly did Dr. Antonio say? So he said he's doing an experiment, a similar type of experiment to what we are doing. Is that?
Yeah, he's doing a size exclusion chromatography as we did, and he's also using the aqueous solution, which is the PBS, as an elution solvent. So I asked Lindsay what exactly a project he's doing, but they have two HPLC systems, the allergen and the waters. So he's doing the one at the allergens, and I'm doing the one with the waters. So yeah, he was giving me a lot of ideas on what I should do, and what I should like do the standard first and then calibration, and step by step. I'm feel pretty good that we'll be able to do the calibration. Do the HPLC and separate the albumin and the dextran pretty well, or which in our case is the BSA. And I can share my screen and give you a little bit idea of what column they has and how the results gonna looks like.
Yep.
Yeah, let me go ahead and share my screen. Can you see my screen?
Mhm.
Try to zoom in. So yeah, so they currently have two columns. The one that we talk about with the lower limit at 10K and the upper limit to 200K, and the other one is a really long column from 6K to 10 million K, from 10 million. So for the bigger one here, it is good to use a pure solution, which means there are only the BSA and there are only the 10K dextran. We can see a pretty good separation from there. But the thing is, the resolution here will be much smaller. It's not gonna get like a pretty accurate of the concentration from what I'm understanding from Dr. Antonio, than this one, than the top one. From the top one, we can get a pretty good idea and accurate result from the smaller tube. So, but for this smaller tube, the only problem is since it has a lower limit of around 10K, Dr. Antonio thinks that if we try to analyze the 10K of the dextran, we probably can't get a good analysis of it, because the 10K would tend to mix or what should I put it? So the 10K will likely to be looks as the molecular, which is less than 10K. So for example, there are 10K, there are 6K or 5K in there. They will be all combined together and eluted at the beginning. But if we can use the 20K as our main dextran, we can get a pretty good idea of the separation that the 20K and the BSA. But the 10K will be not very ideal.
And then I guess the question is, for the dialyzers we're using, do you see any issues in using 15 or 20K dextran?
Yeah, I also asked this question to Dr. Antonio. I said, like, since the 20K is from 15 to 25, it's poorly dispersed. So what if our column can't sieving through the 20 to 25, for example? And he said it should be fine as long as we can capture the part that is sieving through, which is, for example, for our nipple right now, it only sieving the 15 to 20, and it can't sieving through the 20 to 25. It should be okay as long as we have the calibration work and we can get the concentration of just that part. It should be.
So if you're saying that there's going to be a certain. So if you have a dextran you buy from a store,
yeah,
it's going to be between 15 to 25.
Right.
Dalton. That's what you're saying. It's going to be polydispersed. The issue is that only a certain fraction of the dextran will sieve through the dialyzer. And the rest will not sieve because it's too big.
And
right?
that is the case for the Rex C21R, and I'm not quite sure about the Nipro right now. But it gives me an idea that the myoglobin, which is around 17 and 18 kilodalton, will be able to sieving through. So I'm pretty confident about the 15 to 20, but for 20 to 25, I will have to do at least one clearance experiment and run it on HPLC, and then I can give you a clear answer if we can sieving the whole 15 to 25 or not. Yeah, but it should not be the problem. Yeah, using the 20K, and the 20K will be the better option if we try to get like better resolution using this column. But Dr. Go ahead.
No, continue going ahead.
Yeah, Dr. Antonio said if we really want to use the 10K, but in my opinion, like I remember Dr. Maham Nabi, he said like he's quite interested in the 15 kilodalton, and that would be a good representation of the beta 2 microglobin. So I was worried about the 10K might not giving us like a pretty good idea of the beta 2. So that's why I will insist using the 20K as our.
Yeah, the only issue I have is if if only a certain fraction will seep through, how do you get an accurate concentration measurement?
Yeah. So, what I've been thinking is to like we can probably use the dead end mode and then wait long enough of time and going through the membrane, and then after a long enough time the final concentration, the final sample will only be the 15 to 20-ish of the death strand that it can see through, and it will left the 20 to 25 behind if we are running the dead end mode. That's what
Are you sure that's the case though?
Because I mean, like, if it can see through, if the pore is small enough that it can't see portion of it, then I think after a long enough of time, then it reaches stability, reaches steady state, and that would be the only part that can see through. That would be the concentration of. It's like the idea of a filter, is what I'm thinking. But I think your concern is probably right. But yeah, like I said, there are certain chances that the Nipro can see through all the 15 from 25. Yeah. If not, we can.
Can you test it out and see what the seeding is?
Yeah, I can try to see, but all the analyze it will have to be run under the HPLC. Yeah, I can definitely try the dead end mode and use the sieving, and and do one clearance, and I will be able to see if the 25 can sieving through the Nipro. That's not a problem. Yeah.
Yeah, I mean, I the worry I have is,
Yeah, I understand your worry that.
How to infer a concentration, right?
Yeah.
Will you?
Yeah, we can. Yeah, still, like I said, we can still optimize the second one. It can. The 10K should be able to run here, and separate from other thing, but yeah, it's just probably gonna not as good as the first one, and the 10K is still gonna work from separate the 10K from the BSA, using the bottom option. So we can do either way. Yeah.
So I want to ask a simple question.
Yeah.
With the 15 to 25K, do you have an idea what the peaks will look? Do you have an idea what it will look like? Will you actually be able to distinguish?
It's gonna be a span.
Will it look like a broad peak, or will we have several peaks, or what?
It's gonna be one large peak, but there are gonna be like a normal distribution. Yeah, there's a peak and there's going down, so it's have a certain bit of length in between. Yeah, there. Yeah, pretty much like a distribution. And by measuring the area, we can get the concentration.
You'll get the concentration of, essentially, you'll get the concentration of 15 to 25K.
Right.
Dextran.
Right.
And then if you have only a certain fraction sieving through, you will get different concentration.
Yeah,
right?
the concentration of the part sieving through.
You can't tell. From this peak, you can't tell the relative amount of 15 versus 25K versus 20K, right?
Yeah, that's a concern that I had as well. That it's hard to capture the part that is not sieving through. Yeah, but and what I'm saying is we can still use the 10K if that doesn't work. We can use the 10K and use the bottom column here, and we can still get the concentration, but might be not as accurate because it's a really long column, and the 10K is just a really small part that it will have a peak, but the peak will probably be really small that it can't probably I don't know if it can capture the difference of the concentration change or not, but it will have to be, yeah, do the calibration and see. But that's the option.
Yeah, so I guess the question is, do you still think it'll be valuable to do an experiment of 15 to 25K and then just say, just report that this is the concentration for 15 to 25K, and then we can report the clearance of that over time? We have no idea if, within that molecular weight distribution, we have no idea which is being, to what extent is which molecular weight is being seen at a given time. Right?
I think I can should give you a simple idea of how we can tell the differences. So for example, if here are the 15 to 25K dash strand with the with as a calibration, if we are running the sample through the membrane, if we only see a portion of it, if we don't see this peak here, that means there are certain part it didn't see through. But if we see the exact same illusion time and the peak, then that means everything has been see through from 15 to 25. If we only see a portion of it compared to the calibration of just the pure dash strength solution, that means we can tell from there. Does that make sense?
Yeah.
Okay. And the timeline about the HPLC at lower will be, right now today we see if the system is able to work, and we will be getting a result on Monday or Tuesday, and I will talk to Lindsay then, and then we will do if it works, we will do the calibration for the 20K, and also with the 20K with the BSA as well, to get a calibration together as a mixture, and then we will be able to run the clearance experiment and analyze our sample data using the dash strand.
Okay. And with this experiment, are you doing it with BSA or no, not BSA?
Currently, regarding the BSA, regarding any experiment using BSA, we have to wait until the HPLC is set up at lower, and the thing is, should be a feasible solution for us.
Okay.
Yeah. So right now, the experiment I did this week is just myoglobin without BSA, it's just the PBS solution.
Okay.
And yeah, I'm gonna go to the experiment I do today, which is the clearing experiments. And regarding the sieving coefficient, we will have to all the sieving coefficient standard are based on the BSA or blood plasma or blood. So we will have to optimize when we're able to use the HPLC, then we can start the sieving coefficient experiment again. And currently I'm just doing the clearance experiment with just the PBS. So last time we talked about the non-zero ultrafiltration rate that I explained to you. I thought I probably gonna explain to Professor Clark, since he wasn't there last time when I talked about this part. I probably move to our next meeting to just repeat to Professor Clark. So the basic idea is just capture the C out over time and the CT over time, and optimizing when the delta T is approximate to 0, and compared to the total time, the K will be given by this equation here. And before I do the non-zero ultrafiltration experiment, I do the zero ultrafiltration model again using the new dialyzer, which is the Nipro dialyzer, because the previous myoglobin clearing experiments was done by Fassar, and the dialyzer he used is a Rex C21R. So right now we have a new dialyzer. So we do the serial ultrafiltration experiment again. And the condition is the exact same as what Fasar did. The blood flow rate is 200, and dialysate flow rate is 500. And I run it in the conventional mode first, and the initial concentration in the beaker is 0.25 milligram per liter of the myoglobin. And the wavelength that captured in the UV-VIX is the exact same as what Fasar did as well. It's 409 nanometer. Yeah, so showing what Fasar's experiment results is, so he can get fit the data in the exponential curve and get the alpha is 0.092, and my experiments is somehow different from what he did. So saying like I can't exactly replicate what he did, and the alpha value I got is 0.045, about half of what he did. And also,
was this on? So sorry, what dialyzer was this?
This is the Nipro, but I think the problem is not about the different dialyzer, different sieving capability. I think the reason is that from the UV-VIX reading, at the initial concentration, what I'm getting is 0.02, and what he get is 0.883. And I was thinking maybe, I was using the UV-VIX mode as the one that I did with the vitamin B12. And since the myoglobin is some kind of protein, so I was thinking maybe he is using another setting of the UV-VIX. I will probably have to double check with him through the email, or I can I can make some sample solution and run using the UV-VIX, because the initial concentration is way too different from the UV-VIX reading he got compared to mine. Mine is much smaller, but still I can still get the clearance from the UV-VIX setting I have right now. Yeah, but the
Can you try repeating with exactly what Farzad did?
Yeah, I don't know what exactly Fasar did for the myoglobin. He had been using like 3-digit at the beginning and somehow like 2-digit. And yeah, and the other theory is the myoglobin is the lyophilized product stored in the freezing part. So the other explanation is it might be like exposed to the water and it's not working as good as just came out of the bottle, because he was done the experiments back in September last year. I'm sorry, September 2020. Yeah, last year. So it's been quite some time. That might be the lyophilized product is not working as good as just open the bottle. Yeah, that's my second guess. But I'm thinking I'm using the wrong UV-VIX mode than what Fasar did. But this is kind of one of the reasons why I wanted you to replicate what Farzad did, because then you're confident in how you're doing everything. Yeah. So it's important that you replicate, the experiments that Farzad did. Yeah. Were you able to replicate the B12? Yeah, because the B12 he has a experimental protocol written for that, and yeah, everything what he chose but he still didn't mention about what UV-VIX mode, but I'm just chose the one that says UV-VIX. Okay, so you got exactly the same data that he got for the... Yes, same alpha number, same UV-VIX reading. But for myoglobin, you did not get it. I did not get the exact same reading. Yeah, this is a 0.883, and the initial one is 0.2. It's the same I got from the sieving coefficient experiment, but I'm thinking maybe he's running a different mode of the UV-VIX, because this is some kind of protein. Then they have some kind of program for protein as well that I haven't tried it out yet. Okay, why don't you take a couple of measurements? Yeah. I can try that out. Yeah, I can work on the UV-VIX a little bit more. But and hopefully if you can get that soon, so we can resolve this, that would be helpful. Yeah, but the good thing is I think this conventional mode the zero ultrafiltration still can serve as a benchmark of the non-zero ultrafiltration mode experiment that I did coming next. So so calculating the clearance is about half of what facades get, since the alpha value is about half, and and the K is mainly different. It's mainly gonna be dominated by the alpha V here. So the alpha is half, so the K will be approximately the half of what he got. Mm-hmm. So yeah, I want to see like the clearance as a benchmark here. When we're going to the so the ultrafiltration rate I said is around 60, and everything, the blood flow rate, conventional mode, is still the myoglobin starting at 0.25 concentration. Everything is the same except there are a ultrafiltration rate, which means the outlet of the flow rate has been set to 140 to get the 60 of the ultrafiltration rate. Mm-hmm. And that's what we got from to calculate the clearance. So I measure the concentration in the beaker over time, and then I measure the concentration out of the dialyzer, and then I calculated the clearance. So when the concentration of them are the same, the clearance will be the exact same of the ultrafiltration rate. And when they are different, the clearance will be different. And that will all based on this equation here, QB times CT minus the clearance calculation for the dialyzer. So what we got here is like as time move on, the concentration in the beaker is pretty much the same, 0.025, 25, 23, 25, 23, 21, and the concentration out is pretty much the same from what I'm seeing. It's decreasing after 9 to 10 minutes a little bit, but the CT and C out is approximately the same throughout the time. And you can get a pretty good idea here. The blue dot is the CT, and the orange dot is the C out. So you can see it's slightly differences, but there are, at some point, there are like 1 minute, 6 minutes, 7 minutes, and 10 minutes, they are the exact same. And regarding this really small difference, I have doubt that might be the plastic viral that is giving me the wrong number or causing these differences. Mm-hmm. And I also, when I'm testing like around 10 of this viral, I unpack 20 of the new virals, and I test all of this again, and this is what I got. So I'm pretty sure this is the correct UVVix reading that I got here. I'm pretty confident. Yeah, but the other thing is, so we are seeing here, the UVVix reading is about like, so this is 0.2, this is 0.19, this is 0.2, 0.19. It's maybe if the concentration, for example, is 0.195, that is like right in between of the 0.2 and 0.19. So that might be a difference. That is like, so like I said, the concentration difference is really small here. Mm-hmm. Mm-hmm. And my explanation is, since we are running the ultrafiltration at 60, so like Professor Clark said, if we're running the ultrafiltration rate up to 75, we can probably make sure there are no back filtration, which means there are only filtration from the tube to the fiber and no back filtration coming back. If the forward filtration is 60 and back filtration is 0. And what we should be expecting is the CT will be able to equal to C out. But right now the K is the CT is slightly bigger than the C out, like from time to time. So I was thinking maybe there are still back filtration. So for example, the total filtration is 60. So might be the forward filtration is 70 and the back filtration is 10 or even less. But there are still back filtration that is causing the CT is slightly bigger than the C out.
But can you really make that claim that CT is slightly bigger than C out?
It's
because you can't, from the data, you can't tell, right?
you can tell, But can you imagine like we are running only like 140 of the flow rate that is not filtrating out. So when we're running the 200 without ultrafiltration, we are expecting the ultrafiltration. We are expecting the back filtration, right? But right now we are running 20 and 60 is ultrafiltration, which means 140 there is no ultrafiltration. That would be similar to the zero ultrafiltration for the 140. So we are I personally would be expecting the back filtration for the 140 that is not going out of the tube. And that's, I think that's what the...
Okay, sorry, I want you to repeat yourself one more time.
I'm sorry, I'm so sorry.
I didn't quite fully, so go back one slide.
Yeah, let me try to exit through the... Yeah, so here we are seeing that the CT here, the concentration in the beaker, is slightly bigger at some point than the C out. So,
yeah, but I'm saying that we don't know. I mean, you're saying that there's a lot of uncertainty in the measurement. So are you certain it's actually bigger, or is it just basically roughly the same?
I am certain that it's slightly bigger. So what I'm worried about is like, so if this is like 0.20 and this is 0.19, there might be a slightly in between a 0.195 or small difference. But I think this many of dots is be able to tell that the CT is being slightly bigger than the C out. So I think the case on the right is what we are observing right now. And the explanation here I gave is because we know that 60 is the ultrafiltration rate that we set. And there are 140 of the flow rate that is not going out to the fiber, going through the fiber. And I would expecting there is forward filtration and back filtration that is making this not zero ultrafiltration. Even when there are 60 ultrafiltration. And the simulation is possibly is the forward filtration total is 70 and the back filtration is 10. Could be even smaller, but there are back filtration still exists. That's why it's causing the CT is bigger than the C out. Would that make sense to you, Professor Nottingham?
I mean, it makes sense. Although I'm saying that the data, it's not clear just because it's still. I mean, if it is slightly bigger, yeah. I mean, that's an explanation. But it's so slightly bigger, it's hard to know whether it's really, if that's really a significant effect or if it's just like within the error bars.
Yeah. So yeah, I can probably explain it for here. So if the clearance is 60, meaning there are no back filtration. The 20 coming in, 60 through the fiber, and the concentration coming back is the same. So that means the clearance will be the ultrafiltration rate. But if there are more back filtration, the clearance will be larger than the ultrafiltration rate.
No, I understand that, but that's all based on. I'm saying this is all based on your measurements of CT and C out.
Yeah.
And you're saying here, look at the results. Go back. Go back. So I'm saying CT and C out. They're so small. There's such a small difference between them. Can you really say that they're different from each other? Like, what is the uncertainty in your measurement?
The uncertainty of the measurement will be the viral effect. So yeah, sometimes you use a new viral, and for the same solution, it will be better to explain you with the original data. Let me. Yeah, so this is the UVX reading. Let me zoom in a little bit. This line and this line right here.
Yeah.
So the uncertainty is for the same solution for two different viral. it could cause a 0.01 of the difference that I has been observing. But but yeah, but you can also see there are 4 dots that are consistently smaller than the 0.2 here. So I would think that this is not like a thing that is like caused by coincidence. This is not by experimental error, in my opinion, because this is not very likely to happen. And the other possible error is sometimes the UV mix reading, for example, is 0.195 or 0.194. That will become 0.2. But out of all of this error, I think this 0.19 is pretty accurate. It's pretty accurate. I have using different virals, 2 to 3 of the virals, and it's still giving 0.19 of the number. So I am pretty confident.
Okay.
Yeah. Yeah, and the other thing is with this calculation, it requires the delta t equal to 0 compared to the t. So which means the total time should be much bigger than the delta t. But right now the thing I encounter is I can only go up to 10 minutes for the UF for the ultrafiltration rate equal to 60. It's because initially the beaker has 2 liters and we use 1 liter of the solution for priming. So we have the starting volume as 1 liter. And the experiment will stop when the beaker, there are only 400 meters left. There are no, it can't suck out any more of the solution from the beaker, like the very bottom here. So if we're trying to extend the T to make it to 15 or 20 minutes, we have to use a much bigger starting volume, probably 3 liter, so that we can have 1 liter for priming and 2 liter for the ultrafiltration rate to draw the solution out, and maybe we can get the assumption correct here, because since right now we have only 10 minutes, and the delta t.
What is delta t?
Is 1 minute. It's the minute that.
1 minute.
Yeah, it's the minute that we.
And t is roughly 10 minutes.
Yeah, roughly 10 minutes. Yeah. So it's not really good, but yeah, we're expecting we can have a longer, bigger beaker, or maybe we can just priming the 0.5 liter, and we can have the starting volume at 1.5 liter. That might be better, but I'm not sure how the experiment legitimately is better. But that is also one option that we can say 0.5 liter is good for priming.
So when you're doing zero ultrafiltration,
yeah,
this is the same issue, right? When you're doing zero ultrafiltration, the same assumption holds, right?
Yeah, but the good thing
is much greater than delta T.
Yeah, but the good thing is when we're doing zero ultrafiltration, the volume doesn't change. We don't have to stop at 400 liter. What in the beaker is the same, so we don't have to worry about time. We can go forever. But for the ultrafiltration rate, we have to consider the volume has been drawn out of the beaker, and that the volume in the beaker has to be bigger than 400 to continue the experiment. So we can potentially use a bigger beaker, for example 3 liter, to get more time, and then to see to get this assumption correct. Yeah.
If you run for 1.5 years, how long can you run? Experiment.
So it should be a pretty simple calculation. It should be 1.5 minus 0.4, and then divided by 60. I'm sorry. And divided by 0.06. 60. Yeah.
So 1.1 divided by 6.
Yeah, 1.1.
Which is then 20, which is times 100 over 6. Okay, 1.1 times.
About 18 minutes. Then we can go to, if we think that 0.5 liter is good enough for priming, that we can do. and which is about the same case because like when we have like zero ultrafiltration, it might take a longer time to reach the steady state and need a longer volume for priming. But for the ultrafiltration case, it reached the in my opinion, it reached the steady state rather quickly because of the ultrafiltration that the C in and C out in the dialyzer will reach to a constant rather quickly than the non-zero ultrafiltration rate compared to the zero ultrafiltration rate. So I think the the starting volume at 0.5 and 0.5 and 1.5 and the priming volume for 0.5 should be enough for the yeah.
Okay, so what are your thoughts, Q?
Yeah, I think we can increase the sorting volume. That I think that does not change our experimental result. But how about increasing the concentration of the?
Yeah, that can also be the case. Yeah, I think regarding like increasing the concentration, right now it's like the reading is only 0.2, but from
it seems like a little bit smaller.
Yeah.
Are you using the same concentration that Farzad used?
Yes, I'd use the same, but his reading is really good. It's 0.883, so I might have to work more on the UV and see exactly what kind of mode that he used to.
Yeah, you also didn't get oscillatory results. I mean, yours is like, I mean, his is like very clean, and yours is like awesome. Look at yours.
Yeah, but although it's not the exact same with Fasar, but what I'm trying to do is just trying to validate the non-zero ultrafiltration model that this clearance might actually be pretty correct in my opinion. And this method,
You think it's going to be correct?
I think it's pretty good. I would.
Have you done a clearance measurement without recycling and checked?
I can do that. Yeah, but I can do that without recycling and check. Yeah, I can do that.
It may be good to just double check, right?
Yeah,
but you're doing
it's
it
good.
with recycling, but you should maybe do one measurement without. No, you're doing a measurement with recycling, but you may want to do a measurement without recycling and just see how consistent these results are.
Yeah, good point. Yeah, I can certainly do that. Yeah, but I would first evaluate like how many solutions I have to prepare. You might have to prepare a lot, like you mentioned. Yeah, I will have to evaluate that first, and then I will probably do it if it's not a lot of trouble. Right. Yeah, and so this remains the question that I have. If the US rate is equal to the clearance, then I think we can get the answer when we're doing the non-recycle experiment. And and I want to point out one more thing is the clearance experiment needs a lot of the PBS solution. So I might have to order some sodium chloride because it's using a lot of them for each experiment. And then and I might purchase more plastic virals, and I have been using all the new ones, the 20 ones, to guess this number, and I probably for the future, if we want a good validation, I might have to use a new plastic viral if it's like not very expensive. Yeah, and the other thing is that is like stopping me from doing the clearance experiment is the waste collect capacity. So right now we have 5 gallons of the big basket to collect the waste. So I can do like 6 clearance experiments with this 3 basket. But right now I have used like 3 of them, and I can do 3 more clearance experiments. And the reason I brought this up is because the waste picking up the hazard department has been pretty slow. And if we give them the basket to get rid of the waste, it might have to get me to wait a week to get my basket back so that I can collect the waste again. and that's the
Really?
and the
What do other labs do for this? I mean, I thought that this is the waste people. They should come whenever they should come often.
yeah, they come pretty often, but I actually meet them today. So I submit the request on, I think it's Wednesday night, and I'm sorry, on Tuesday, and then they didn't come Wednesday. They come today at around 3 o'clock, and they come pick it up and said we might have to expect the basket back next week sometime, about a week. Yeah, that's what he said. And if we're trying to like
How expensive? How expensive are these baskets? You get more baskets.
around $15 per basket.
$15.
Yeah, we can. So for 15.
That's fine. Just get more baskets.
Yeah.
I don't see any issue. Do you see any issue getting more baskets? This is the biggest issue?
It's not really like a big issue. It's really depends on like how many experiments you're trying to do, and yeah. Okay.
Just get more baskets. If this is like hampering your ability to research and it's that cheap, just get more baskets.
Okay. Great. Yeah. So yeah, I will continue on the validation of the non-zero ultrafiltration experiment.
Yeah, check your UV viz. I mean,
Yeah, I can definitely do that.
I'm surprised that you're getting such low reportings. That shouldn't be the case. You should, if you can email Farzad, ask him like, what the deal is with the myoglobin.
Okay. Yeah, absolutely. Yeah, I think that's.
Yeah.
Do you have any like further questions regarding the experiment or what you want me to do?
I mean, I think you need to be able to get these experiment clearance measurements. You need to be confident in all these clearance measurements before you can do anything else, right?
I know. Yeah, I have been like using a lot of new plastic virals and double check on this thing. So for one dot,
using the new plastic vials, are you running into these issues now with the UV vis measurements, or are you still? Because you remember you had when you're using the old plastic vials, you had some of the measurements were corrupted and you get the spikes.
Yeah, I get rid of that. I get rid of the one with a spike. To me, the plastic virals, like I don't reuse them. I just reuse the one that is not giving me a spike. But
no, but I'm saying you bought new vials, right?
I didn't buy it. It was already there. So there was a total of 80 of the virals that has come to the package, and Fasar left me with around 40. So 20 is like they haven't opened it yet. The package, it was still with the packages. So I think this is where's my confidence is because I just open the package and then I use it, and then I guess this little bit dark, and then I compare with using different virals and see if the number sticks, then this is the number,
So are you confident now, at least in the vials, that you're not going to get bad results?
Yeah, I'm confident, as long as I can double check with new virals.
Yeah, so I think the main thing is you need to just make sure you get the same UV vis measurements that Farzad did with the myoglobin.
Okay.
Is there an expiration date on this myoglobin?
It didn't say, but it's a lifelike product. It's I didn't know what it was like. Right, open the bottle, what it's gonna look like. So I can't tell the difference if it's corrupted or hydrated.
Yeah.
So
is there any guidelines listed on the MSDS or what's listed even in
I can check
online? Yeah, you may want to double check too. If there's, because some materials, I mean, it's if you keep it for a while, it gets corrupted. I don't know about this, but you can just double check that too.
True. Yeah, certainly. Yeah, I can see what typically UV-VIX value people get from myoglobin as well. Yeah.
Yeah. Q, do you have any comments you want to make?
No.
Okay.
Yeah, maybe we need to double check the UV figure.
Yeah, you have to double check the UV vis, and I think you have to also, I believe, check if these clearance measurements are the same as if you were just to do a knot recycling, right?
Yeah, I'll certainly do
Yeah.
that. I would
Because that's
certainly.
a standard way most people measure clearance, right?
Yeah,
Without
yeah,
in ultrafiltration.
right. Yeah, I'll certainly do that experiment to double check with my result here.
Yeah.
Right.
Yeah, maybe if we don't have any backfiltration, then that the clearance will be same as the reverse filtration, right? So the clearance level generally something like the amount of the
I mean, one thing.
Yep.
Go ahead, Q. Sorry, I didn't mean to continue.
So it is like some the amount of the clear fluid inside input into the system, human body. So the clearance will be same as the ultrafiltration, like if the concentration is same as the in the concentration.
Yeah. I mean, one thing you can check about back filtrations occurring. Do you know you have pressure? You have your pressure gauges, right?
Yeah.
Did you record your pressures during this experiment? If you have, you can see what the pressures. Look, if you know what the inlet and outlet pressure are on the blood side and the inlet and outlet pressure on the dialysate side, it's going to be roughly a linear pressure drop, a linear drop in pressure. And so you can plot the pressures and see if there's an intersection, right? If there's an intersection, then you would expect that's roughly where the point of back filtration is.
But I thought that might not be really accurate from the previous meeting that I had with you guys. We talking about Alex's experiment, that it might not be the exact
So
point.
that's not necessarily true if you have lots of proteins in your solution, because you'll have osmotic pressure, right?
Yeah, yeah.
The osmotic pressure will change the so if there's, for example, if the membrane is semi-permeable, then if you have accumulation of solutes that cannot permeate the membrane, that'll lead to a buildup in osmotic pressure, and it'll change the flux.
Okay.
But I mean, that's generally the case only when you have lots of protein, right? I mean, what is the concentration you're dealing with?
It's really
here?
small.
Probably
Yeah, it's really small.
So what is the concentration? CRT is going to be the pressure, osmotic pressure, roughly. Concentration times natural gas constant times temperature. You should be able to estimate that is.
Okay.
And how big is that compared to the pressure drops you're examining?
Yeah.
You should probably, if you do a quick calculation, CRT compared to the pressure drop, if it's really small, then you know that the osmotic pressure is not really playing a role. And then you can just do the standard calculation where you just do a linear pressure drop across the two, and you can see where the intersection is, see the point of back filtration, right?
Yeah.
So you can do these calculations and get an idea if this is true, right? So I don't know, you can record the pressures and see what happens. If that's the case, then yeah, I mean, if there was no back filtration, yeah, this is probably correct.
Yeah, I didn't record it, but from what I see is really the pressure drop differences is really small. So yeah, that might be that will make the pressure drop point, the back filtration point, really at the end. So then it might be around here if there are back ultrafiltration. So yeah, because the pressure drop is really, really little.
Yeah, so you can check what the pressures are, right?
Okay.
The outlet pressures. For both the dialysate and the blood. That'll give you an idea there is going to be a point of back filtration. If that's the case, then if that isn't the case, then that means your hypothesis is probably correct, right?
Okay. Yeah. Yeah, I'll do the osmotic pressure and then see how much is it for the myoglobin, and see if it's gonna affect.
Yeah. So this is So do that, and you can also just if you assume there's no osmotic pressure, so you can see if there's a crossover point for back filtration. If there isn't, then your hypothesis is probably true, correct?
Okay.
And then obviously you may have to design your study such that you do see some maybe back filtration.
How I like can't really see like how I can like measure the back filtration.
You can adjust the pressure, right, of your valves, or no?
We could adjust the pressure like what Alex did. Yeah, but I think like this is a pretty good, I don't know, like good validation for the back filtration. But I can see if there are any other way to examine that.
Okay.
Yeah, I'll think about that.
Yeah, just think about these things.
Okay.
Yep. Okay.
All right.
Yeah. So just maybe you can send me emails about some of these things as you're getting it along. So hopefully, if you have any issues, we can kind of nip it in the bud earlier, right?
Okay. Yeah.
And you can share with Q too. Maybe he can also like give some feedback.
Yeah.
Earlier.
Absolutely. All right.
Okay. Sounds good.
All right. Thank you, Professor.
Anything else you want to discuss?
Nope.
Okay. Sounds good.
All right.
Okay.
Yeah. See
Thanks.
you next meeting.
Yeah.
Okay.
Thank
Bye.
you.
Okay.
Thank you, Q.
Okay. Bye.
Bye.
Bye.